Okay, so moving on, we're going to cover next chapter 8 in our textbook. It will be on planning and learning, or more precisely, we're going to cover some model-based approaches. We'll try to learn a model of the MDP, and then use that model in order to plan or to better plan ahead. Some to-dos, please be sure to be on top of your assignments. First of all, quizzes. You have the Monte Carlo control quiz, the TD learning quiz, the N-step bootstrapping quiz. With respect to assignment implementation, please be sure that you finished by now or are towards finishing implementation of value iteration, asynchronous value iteration, policy iteration, Monte Carlo control with important sampling, tabular Q-learning, SARSA, and with respect to the course project, you should start converging on your project proposal. So both the domain or the problem that you are tackling and your research questions, something that can be answered by running some experiments. Okay, so reiterating what we learned so far with respect to different approaches to solve MDPs. So first of all, we saw a dynamic programming approach, which is of policy. It doesn't require any specific policy or doesn't assume that we follow a specific policy. That is, actually, we don't follow a policy. We solve the MDP offline. We don't interact with the environment. It performs local learning by propagating values from neighbors. However, it does assume, or all of these solutions assume that we know the model, the transition probabilities, and the reward function. Then we saw an online approach, that is the Monte Carlo approach. It is on policy. That is, it is highly sensitive to the policy used in order to interact with the environment, and we can usually learn Q value or state values. In that we saw Q values, but we can do the same with the state values that are relevant to the specific policy that we're using in order to sample the trajectories. Monte Carlo approaches require full episode to train on. However, they are model-free. That's the first model-free approach, reinforcement learning approach that we encountered. Next, we saw TD learning. This is an extension of dynamic programming, so we can do value iteration or Q value iteration in an online way. We're assuming that each transition is a sample of the Bellman update rule. So this approach, one-step TD learning, is off policy for Q learning. Similar to dynamic programming, it performs local learning, propagating values from neighbors, also known as bootstrapping. However, it has an issue with very slow value propagation and also with biased value propagation, right? Because of the bootstrapping, because we compute the target Q value based on estimation in the next states, we introduce some biases into the equations. But as before, this is, as with the Monte Carlo approach, this is model-free, unlike the dynamic programming approaches. And finally, we saw an approach that combined both the Monte Carlo, the generalized on top of Monte Carlo and TD learning, where Monte Carlo and TD learning and one-step TD learning are the two extremes of some n-step TD learning framework that allows us to bootstrap results by observing n observed rewards and then doing approximation at the nth step, right? By doing so, we hope to balance between the bias introduced at the TD learning with the TD learning approach and the variance introduced by a Monte Carlo approach. So similar to TD learning, this performs local learning with flexible locality, right? The n represents the locality parameter. It is model-free, however, it is on policy. But similar to the Monte Carlo approach, we can also integrate important sampling and allow it to be of policy. So finally, all of the models we've seen so far for reinforcement learning, the three main approaches, TD learning, Monte Carlo, and the generalized n-step TD learning, all of these we said that they are model-free as opposed to dynamic programming, which is model-based. But then what I would like to discuss today is, must online solvers, reinforcement learning solvers, be model-free? In that case, can we use a model in order to speed up or to improve learning for online solvers? What do you think?
Yes.
Yeah, else we wouldn't have a topic on that, right?
But I do have a question. If we do have a model, why do we need an online solver? We can just use dynamic programming.
That's a good question, actually. Yeah, that is a good question. If we do have a model, then we don't need the online solvers. That's true. But the question would be, how do we get a model? Okay, we'll get there in a second. And then, how much effort do we spend in getting a model? And then, what might we do with that? And how good is the model, right? Is the model that is our approximation? We'll only approximate a model.
Yeah, maybe it's not good enough for dynamic programming.
For instance, okay, but we'll discuss this today, right? So in any case, we know that having a model is useful. It will allow us to solve a problem offline, right? An MDP offline, without the pain of interacting with the environment. And we can, of course, we can simulate episodes cheaply and do reinforcement learning. And as I said, we can compute the optimal policy offline. So there's no growing pains. But even for the online solvers, we can simulate transitions very cheaply and very quickly. So yeah, that sounds great. And you might say, okay, we should definitely use model-based reinforcement learning. But, well, as I said at the second lecture, I think, we forgo the assumption about knowing a model. So after we discussed dynamic programming, we said, okay, that's it. We'll assume to not know the model moving forward, right? And we're doing online reinforcement learning. So we don't know the model, but then the question might be, can we learn the model? That is the transition and reward functions. Sure. So obviously we can learn the model, but we just need to observe enough relevant transitions, right? If we observe enough transitions, we can approximate our transition probabilities and the reward function just by observing the rewards, right? So let's build a model. So when we interact with the environment, we observe transitions, right? Each transition is state, action, reward, and the next state. Usually that's enough to provide us with all of the information that we need because of
the Markovian property.
The Markovian property, correct. That is, I don't care about the states that we visited previously or that we'll visit later. They will not impact the transition probability between SA to SI plus 1 to the next state, right? And it will not impact also the immediate reward RI plus 1 here. Okay, so how can we learn the transition probabilities? Simply, we'll set our approximation of our estimation of the transition probabilities for any S prime pair, so the probability of arriving at S prime, given that we are at state S and performing action A, simply as the number of times we arrived at S prime over the number of times we actually visited that state and action pair. Okay, so capital N here is the number of observations that includes evident X and Y and Z, all of the evidence in parentheses. Okay, so N, S, A, S prime is the number of events where we saw S, A, S prime. Hopefully you remember this notation. And learning a reward function is just as easy. So for each state and action pair, we can approximate or estimate our reward function as the mean of all of the rewards that we've seen previously by being at state S and taking action A. Once we learned these values, right, we converged on these probabilities and on these rewards, we can solve the problem offline. What's the problem now? That we need a lot of transitions, right? I mean, we need a lot of transitions in order to correctly approximate the model. To a point that it might be faster to just do Q-learning or model-free approaches, might be faster than learning a model and then solving it offline. So, as we said, so far a model allows offline planning, but learning a model is done online. I mean, if we assume not to know it and to learn it from interaction with the environment. So now you might ask, well, how many samples are required to learn an accurate enough model? It can be arbitrarily large, right? Arbitrarily large, specifically if you have rare events. Okay, so you might ask how many samples are required to learn a useful model? Maybe one that doesn't include the rare event, but maybe they don't really matter. Well, that again is very domain dependent. It depends on the model that we are trying to learn and the reward distribution. Right? For instance, if you're trying to learn the expected reward from buying a Powerball ticket, well, you'll have to buy a lot of these until you actually observe one win. It's a very rare event, but with very large reward or different reward that might skew the entire reward estimation, right? But that would be an example of a model that will be very hard to learn. It will require a lot of samples. Finally, eventually, it's important to remember that a model is just a model. So a model inherently contains some errors or some blind spots that we must be aware of when we use it to train a policy. So another question that we might ask is, can we train a model for free? So we understand that it might cost us a lot. It might be very expensive to train a model. But then you might ask, well, can we do it for free such that it doesn't require us a lot of resource or a lot of samples? And the answer is yes. Specifically, if you're running a model-free algorithm, you're producing relevant transition samples, right? So why not use you can use these transition functions to train your model for free. It won't cost you more, and you'll get an approximation of the model. So let's do exactly that. Let's use these observations to learn a model, because, well, it's free and it might be useful. Maybe not, but we didn't pay extra for that. So let's see if this is a powerful tool or something that might be useful moving forward. So these are just some results showing let's say the accuracy of training a model just by observing transition. So these results are from two Mujuku environments. So Mujuku is a physics environment where you can simulate different types of robots, for instance. So here you have the robot on the left is a hopper. It's a simple robot with one leg that needs to stand up and then move forward, and on the right it's a two-legged bipedal walker that can actually use two legs in order to balance himself and walk forward.
Bipedal walker is a different domain.
So how do you call this one?
This is Walker 2D. So
Walker 2D.
There's also bipedal walker, so that's another domain.
That's the OpenAI GM. Yeah. But isn't it also the same robot?
It's two legs, it's just they're named different. Yeah.
Okay. So this is just a Walker 2D, officially, right, by OpenAI. Okay, so here, these are results where different policies were used just to interact with the environment. So actually, specific policies that were used in order to train models such that allow these robots to move forward. And then, what they did here in this paper, they collected transitions by applying that a specific policy to the domain, collecting the transitions, and then using these transitions, as we saw previously, to train a model, the transition probabilities and the reward function. And here these results for the Hopper and the Walker 2D show you the accuracy of the trained model in predicting a trajectory, state and rewards, for a different policy, right? Or let's say for various different policies. So on the y-axis here, you'll see the prediction error. It starts from a low one, and it's you can see that this is a log scale, so the error at the top, the error difference, is much larger than the error difference at the bottom, okay? Hopefully you're familiar with log scales. And on the x-axis is the policy shift. So this represents the difference between the policy that was used to sample the environment, to get the samples for training our model, versus the models that was used when we interact with the environment and try to predict the outcome of each step. So as we expect, if the policy that we are using to predict, to try and predict the future, the state evolution, differs more from the policy that was used to collect the samples for training, then as expected, the error increases. Okay, so the state that we encounter are becoming more and more different because we're using a different policy. Finally, the different colors of the curves represent different amount of training data, right? So for instance, we can run a single trajectory in the environment and get like 5K samples and train our model based on that, or we can run several such trajectories, sample several episodes and get a lot more transition samples. And as expected, if you have a lot more transition samples, your accuracy is better, right? So that's the yellow curve, for instance, is much lower than the purple curve. So this shows us that we can use observations in order to train a model of the environment. And that model can be fairly good, specifically if we have a lot of samples, if we see a lot of these samples, and specifically if the policy that we use to collect those samples is similar to the policy that we're using to the policy that we're trying to predict what will happen in the environment if we use that policy. And these two facts actually make sense. So the takeaway message here is that it can be done if you sample enough and if your policy is close enough. However, if your policy is far away from the policy that was used to train your model, and if you don't have a lot of samples, well, then your approximation, the model approximation is not great, and probably you shouldn't rely on that, right? But even good models, by the way, even those the most accurate ones, they will still have error, okay? It's important to understand that a model is just a model. So at the end of the day, we have to take it with a grain of salt. Any questions? Makes sense, right?
Yes.
I mean, yeah, these are sensible results.